The main objective of this framework is to design and develop an artificial intelligence autonomous vehicle controller platform. Here I am in the spectacular city of Medellin Software Valley. Medellin is characterized as the most innovative city of the world. From my design center in the beautiful city of Medellin, actually from my research and development design center in beautiful city of Medellin, I have included and tested and engineering prototypes. Included in this workload are the software scripts and the machine learning algorithms and the neuromorphic architecture explanation.
The framework of this video shows the implementation of a sophisticated artificial intelligence autonomous vehicle platform. Here I used advanced computer vision methodology to distinguish different objects, colors, and natural surroundings of the environment, and can apply sensors. The system architecture consists of a top layer hardware, a middle layer hardware, and a lower layer hardware. It also includes radio telemetry and radio control system and power management. So the lower layer of the architecture includes motors and the motor drivers. This layer is responsible for the propulsion and the steering of the robot. In this case, the artificial intelligence vehicle system is the middle hardware layer, provides the system with its autonomous movement and path planning capabilities. In order to provide communication, redundancy, and remote control, the system was equipped with several communication systems which are under the control of the autopilot. Some of these systems, like the GPS, are part of the second layer, that is the middle layer hardware, and are directly used by the autopilot subsystem. The telemetry system and the remote control receiver are communicating with the autopilot board using different interfaces. The top layer of the architecture includes the microcomputer and an optical camera, which are needed for the computer vision tasks. The propulsion system of the autonomous vehicle is implemented using two brushed DC motors with integrated encoders. They have metal gearboxes and are intended for operation at a nominal voltage of 12 volts. The motors have gear ratio of 19:1, which provides 500 RPM without a load. For turning left and right, I used the smart steering servo motor. In order to perform object detection, I use deep neural classification models. Their convolutional layers are the key component which enables image processing and object detection. These are filters which extract features from the previous layers in order to transform the input data in a form that is more useful for representation. The workflow for the training of the system to recognize the environment of the application, I use the TensorFlow Object Detection API, which I used as a training platform. The workflow contains 4 main stages: preparation of the environment, preparation of the data sheets and data sets, training, and then implementation of the object detection model. The input data set is required to contain images that have objects of interest related to this application. In order to train a good detection model, TensorFlow requires hundreds of thousands of images. However, instead of training a model from scratch, it's possible to retrain a pre-trained neural network model and then use smaller amounts of images. The visual odometry is a technique for autonomous navigation, motion tracking, and obstacle detection and avoidance. It also allows the robotic vehicle to localize itself by using only a stream of images captured by the camera, which is attached to the outside system. Several small form factor computer boards were used in the implementation of this autonomous vehicle. A small microcomputer, which is the core of the top-level hardware layer of the smart vehicle platform, supports several cameras, including the commercially available cameras and other advanced real-sense depth and tracking video camera systems. These systems are used in order to detect different colors and also develop a custom Python script that allows the detection of specific predefined colors. I also used OpenCV to run the programming scripts. The computer vision algorithm is set to recognize different colors, such as red and green. During the mission, the computer vision algorithm is running constantly on the artificial intelligence vehicle controlling system. An additional benefit of the visual navigation system is the fact that the smart vehicle can track rows of objects in the field completely autonomously.
The artificial intelligence vehicle controller system. The DC motors are connected to the driver board. The drivers are installed in a mirror configuration, so it is required to reverse the polarity of the power supply to one of the motors because of the reasoning that the motors are DC. The change of polarity will reverse the direction of rotation of the motor shaft and will synchronize the direction of the rotation of both motors. The main neuromorphic architecture and CPU. Autopilot controls the motor driver via the pulse width modulation signals, that is, the PWM signals. These signals have different levels in order to determine the direction and movement. A high-level signal will drive the artificial intelligence vehicle system forward, while a low-level signal will drive the artificial intelligence robotic vehicle backwards. The main controller controls all the hardware components of the middle layer, that is layer 2, which are above the DC motors, the motor driver shield, and the servo controller. Also, the primary GPS and compass are required to provide the autopilot with positioning data during movement, while the secondary GPS system is an optional component and is normally used to improve localization precision. Here is a synopsis of the servo motor application with respect to the artificial intelligence autonomous vehicle prototype. So, a servo motor is a motor whose shaft position can be set using an external control signal. With a standard servo motor, that control signal is a logic level pulse width modulation waveform, PWM. The pulse width of the PWM waveform is how the servo positions its controller. Internally, a servo motor consists of a DC motor driven by a controller, and the controller takes in the pulse width modulation signal, measures its pulse width, and turns the motor accordingly. The key to making all motors work is that the motor shaft is coupled to a sensor which reads the motor position. This position information is fed back to the controller, the CPU mainboard, which then makes the correct adjustments to the motor speed and direction. Servo motor driver software methodology. So you need to include the PID library. Then set the PID gain variables by fine-tuning proportional gain, integral gain and derivative gain. Now let's set the PID parameter variables, such as setting point, setting the input, and set the output. Let's create a PID object. Declare the variables for pulse width calculations. Then declare timestamp variables, followed by servo pulse width modulation PWM pin number. Now let's set the width output pin number as it is indicated on the software module presented in this video. Set the motor drive direction pin number. Then set the analog to digital converter resolution to 12 bits and initialize the PID controller. Then set the mode, set the output, and set sample time. Now let's run the PID process to get output value. It's also indicated and illustrated in the software module and the software model presented in the video. And move motion forward for motor direction and set the direction to forward as well. Now let's move the motor in reverse. So write the pulse width modulation PWM to motor driver and then set direction to reverse. That culminates the software methodology and a synopsis of the software module and model presented in this project. A critical aspect of this design is based on a PID controller that is a proportional integral derivative system. The PID controller is a control mechanism that employs feedback to apply a correction to its output value, also known as a three-term controller. So the proportional integral derivative have to be used in this specific application. The PID controller is a closed loop system, which I have explained and illustrated in this video, meaning that the final output is fed back to the input. If the output does not match the desired input, then a correction signal is applied in order to eliminate the errors. The input to the PID controller is called set point. In the case of the servo motor controller, the set point is the desired position of the motor shaft as indicated in the software scripts explained during this presentation. The measured output of the PID control system is known as a process variable, which is also illustrated in some of the block diagrams with respect to the PID unit. The servo controller design would be the threading from the potentiometer. The differences between the set point and the process variable, as illustrated in the software, is called an error value. Here is a synopsis of the different software models and scripts and algorithms implemented in this project. Okay, let's declare a number of variables that will be used to calculate the pulse width. The use of the volatile statement preceding some of the variable definitions. It is used to load the variable into the system memory, RAM, random access memory, instead of a register. And it is a normal practice when the variable is being modified within an interrupt handler. So now let's define variables to hold the timestamps, which will be used to calculate the pulse width, and then define the pin number we are using to receive the pulse width modulation pulses, the PWM, from our servo controller. In this setup, I set the incoming pulse width modulation pin as an input and also initialize the serial monitor. The setup is also a statement to attach the interrupt to the interrupt handler function. Measure pulse. The change parameter, which indicates that the software is calling the interrupt handler every time the statement of the pin changes. So now let's call the interrupt handler at both the beginning and the end of the pulse. Now let's take a look at the measure pulse function itself, which is the objective of getting this process to work. This is the function call every time the pulse changes states. The loop is not complicated at all. Here I check to see that the interval between pulses has elapsed, and if it has, we print the value of the pulse width modulation underscore period variable.